resolved. Okay. So I was just saying, my personal research is in electron microscopy and defects in materials. So it does have some relationship to the material science end of the spectrum. I think in today's panel, we'll get more into application spaces and really the pulls on the technology, whereas often we think about what we do at the university being pushes in technology and bringing new ideas to this space. But let me start with our panelists. I'll first going to introduce our panelists, tell you where they're from. You'll see we have an array of people from companies, from academia, and from some of our federal labs. I'll start with make sure I get this right. I didn't have them sit in a particular order. So Blake Johnson from the quantum platform at IBM Quantum. So maybe Blake, you can share with us a little bit about your position in IBM. I know you spoke earlier today, but for new people in the audience, tell us a little bit about yourself in relationship to quantum initiatives.
Sure. So I've been at IBM about 3 years, and I'm responsible broadly for the layer of the software layer and sort of execution layer that sits above the quantum hardware, where we're trying to pull in various different techniques, of course, to extend the power of what the computer can do, and to make it easier to consume for a user. It's the kind of the part of the mission, the broader IBM quantum mission that I lead, is we're trying to make quantum computing accessible and available to people to solve real problems.
Okay, thank you. And then I believe we have Jonathan Wormald next on the panel, who's representing the Naval Nuclear Laboratory.
So I'm Jonathan Wormald. Naval Nuclear Laboratory develops advanced naval nuclear propulsion technology for safety and reliability of our Navy's submarine and aircraft carrier fleets. My role at the company is in material science problems, especially as it relates to electronic structure theory and other atomistic techniques, as well as radiation transport and radiation matter interactions.
Okay. Thank you very much for joining us. We also have Joshua Smith from OPeTechnologies.
Yes, my name is Joshua Smith. I am the president of OPeTechnologies. Being a smaller company, I'm involved in just about everything. But our company specifically has done research and development in optical analog computing and optical encryption devices. And we're starting to get more involved in the research in quantum computing, and thus me being here. And yeah, glad to be here.
Thank you very much. We also have David Bernal, who is in quantum computing at NASA University Space Research Association.
That's right. Hey, everyone. I'm David Bernal. I'm an associate scientist at the Research Institute of Advanced Computer Science at the University Space Research Association. I'm also part of the Quantum Artificial Intelligence Laboratory from the NASA Ames Research Center. I'm currently working on developing and benchmarking algorithms to solve optimization problems using novel computational tools, including quantum computing. And yeah, that's my involvement with the Quail group, as we like to call it. And I'm glad to be here.
Thank you for joining us. And finally, we have Sridhar Tayur, who's the Ford Distinguished Research Chair and University Professor of Operations Management at Carnegie Mellon's Tepper School of Business. And Professor Tayur was very instrumental in the tutorial workshop that we held on Monday, and has a tremendous amount of interactions with business and has a unique perspective. So please introduce yourself.
Thanks, Beth. Yes, I'm a business school professor, largely interested in solving large-scale optimization problems. For 10 years, I was the founder and CEO of a software company. A lot of the supply chains run off that code today. So when quantum computing came along, I wanted to see what can quantum computing kind of do for various types of large scale optimization problems. My personal research interest that included David while he was a student here, was to see if before quantum computers are here, can we do something that's quantum inspired computing? And so that's kind of my involvement with the quantum and PQI space.
All right. Thank you very much for joining us. So we're going to have this have open questions. If you're on Zoom, I'm going to monitor the chat. If you have questions, if you're participating remotely or people in the room, feel free to raise your hand at any time. I think, we had the opportunity to get input from a pretty diverse community on, specific questions, learning from them about opportunity spaces in quantum information sciences, but also it's an opportunity for us to get feedback from them on how PQI can help serve the broader community outside of the academic institutions. So just feel free to raise your hand if you have questions or comments. And again, I'll monitor the chat on Zoom. But I might kick off asking a question, and we can kind of go down the line. If you have a response, please respond. But maybe you can articulate from your perspective maybe one of the big challenges or opportunity spaces that you see for quantum, and if you can articulate a grand challenge or opportunity from your perspective, we'd like to hear your thoughts on that.
From my perspective, one of the major challenges we face is marrying the needs of applications and the requirements of how powerful the quantum systems need to be with the capability of what we can deliver on the timescale before sort of an investment community loses interest. And that doesn't, investment communities broadly, not just like venture capital, but also in sort of internal investment operations within large companies, large and small. Because there's a great deal of promise, but it needs to deliver before people sort of move on to the next thing. And so for me, like pushing both on terms of finding novel ways to reduce resource requirements for applications is kind of a critical piece to try to intersect with what I hope are ambitious plans in terms of extending the reach of hardware systems. And I want those things to meet. I want them to meet in the coming decade.
We're kind of interested in two areas of quantum technology. And quantum computing, we're really interested in algorithm development and how it can be made to be useful for engineering applications, whether that's materials, engineering mechanics, thermal hydraulics, radiation transport. The other side is we're interested in quantum sensors and how those can be made for extreme environments, whether that's temperature, corrosion, radiation, and last in those environments for long time scales on the years to decades.
Yeah, so we're fairly new in the quantum space. I'm kind of along the lines of Dr. Youngblood that spoke earlier, being very involved in the photonics space and more classical style computing, or even analog, more classical than classical. And however, one concern we always have in the R&D space is piquing the interest of either investors or other potential programs that we can get involved with, and having that more of a future scalability in the quantum space. And whenever there's a lack of really great foundation on a lot of different pieces, it's hard to be able to show where deliverables can be actually pursued. So that's a difficulty. However, connecting with groups such as PQI is really great to be able to gather knowledge and work with different potential groups that we can help make it more versatile and attractive to potential investments and things like that.
So yeah, our team, we are algorithm developers. We work closely with academia and with industry, hardware vendors, for example. I'm gonna go a little bit orthogonal and say one of the big challenges that this field currently faces is we need more people. There needs to be and I'm glad that we're in such an event like this, because the workforce development is something that we're already noticing. We don't have enough people to do all the things that we want to do. So we can keep talking about the science later, but that is something that I really want to bring up to this audience.
Yeah, I think of it in three buckets. One is what applications are most suited for this new technology. I think there are some applications that are being served quite well with classical methods, and there's no need to revisit those. And so part of what I've been trying to do is work closely with industry. I work closely with, let's say, a financial firm, and try to identify problems that they wish they can solve better or faster, and see if that matches to the capabilities of what quantum or quantum-inspired computing to do. So I think about finding the appropriate application basis. That's one piece from algorithm development and application space. I also happen to be a venture capitalist, so I'm a LP of a venture capital firm. We have about 450 million that we put into companies, and over the last year and a half or so, we've been seeing CEO pitches from this quantum side. We haven't made any investments. I have one more call tomorrow to see. So my other interest in quantum is to look at the various startups that are coming up for seed funding or Series A funding, with different types of qubits or different types of connectivity, or things of that type, and try to better understand which technologies have, in some sense, the most reasonable promise. So I think of those two as one as a professor and one basically as an investor.
Okay, thank you. Any follow-up questions from the audience? Yes, please. Yeah, so I think the question was, I'll repeat it, is does anybody have examples of very near-term applications that you kind of see, like the low-hanging fruit maybe? Or feel free to raise your hand if.
I did one last year, not because I was solving it on quantum, but it was quantum inspired in the sense that this is a hedge fund, and they're always looking for something that works faster and gives them better answers. And so a student of CMU who works in that, and I worked on a project for 6 months, and we found that there is one application they have. I talked about it during the tutorial on how they decide how to use market signals they get from machine learning algorithms to make the investment for the day. It's an alpha kind of optimal combination problem. And we found that quantum inspired algorithms was able to give them better answers than what they were doing. So I think there are these niche applications, but I think we need to find broad-based industry and broad-based class of problems that I think can benefit from it. So I think there are hand cherry-picked examples. I think you have worked on some, David, yourself with Exxon. So
Right. Yeah. You read my mind actually, and the presentation earlier by IBM, it reminded. So I used to work at the ExxonMobil group that collaborated with IBM, and also bringing my background as a chemical engineer. The quote unquote low hanging fruit that many people think might be one of the first places where quantum might make a big impact is quantum chemistry, right? And the prediction of behavior at the molecular level, at the atomistic level, is something that where we first can prove theoretically some kind of exponential speed up, and second, like it seems that we don't need those many resources compared to other applications such as cryptography, for example. So this is not only me saying that, but I don't know, McKinsey and the Boston Consulting Group, they also tend to believe that this is going to be one of those, again, quote unquote, low hanging fruits. By low hanging fruit in quantum computing, it might be pretty high up, but still though, yeah.
I'll add something. So I do think the things that are kind of simulating nature are probably the things which have the least kind of encoding overhead for expressing as in a quantum circuit in an algorithm. And that feels like, at least today, an important factor in being able to fit your a problem of sufficient size onto the hardware that's available. And so like chemistry is something that we throw around a lot. It looks better than some other places, but there's still some ways in which it's, at least the methods we have today are a bit scary from a resource perspective, right? It's polynomial, but it's like a end of the 8th or end of the 10, right? So like that's still kind of a scary polynomial, right? So, but some of the things which are more like condensed matter systems, or really trying to simulate behavior of surfaces or solids, may have lower encoding overheads because you're sort of directly trying to simulate a Hamiltonian, or the time evolution of the physical system. And so you have a more sort of direct encoding to the lattices of the various hardware platforms.
Okay, thank you. Yeah, Rod, please.
I want to go into the workforce development question.
Sure.
So, Wednesday, we talked about a brand new undergraduate quantum computing degree that it will offer just now. So I'm excited for that. Worried because I want to make sure that like graduate students, they'll have good jobs. And so I wanted to hear, what's your perspective on potential jobs at the undergraduate, master's, PhD levels?
Sure, I guess I'll take it since I brought the topic out. Yeah.
Yeah, maybe I'll just repeat the question for the people who are participating on Zoom. So the question was about workforce development, the new degree program at Pitt, and what is the job market, and what's the demand for students being trained in this particular area?
Sure. So again, I come here on behalf of this University Space Research Association. This organization was created. Its original intent was to share knowledge, initially from lunar rocks, with as many universities as it could be possible. So it's deeply related to the organization that I represent, the part of workforce development. I believe, again, there were a couple previous talks in this conference. The talk from the NSF officer was showing us like how much money and desire there is right now here in the United States for people with this kind of knowledge. So what I can tell you from, let's say, a more personal experience, we don't get as many internship applications as we wanted, because most people are going to IBM, to Google, to all the other companies. So there, at least we would like more people to be involved in this. And these are exciting jobs. These are good jobs. These are jobs that sometimes do require a little bit more specific training than what's usually found out there. I think it was said before, a computer science degree might not be enough by itself. Physics degree might not be enough by itself. So this sort of intersection is something that is very desired right now, at least from our side.
Jump in on that topic too is, the kinds of quantum computing right now for the foreseeable future is very interdisciplinary in the context of our old models of sort of splitting up disciplines, right? And it may have emerged out of the laboratory of physics departments or applied physics departments, but the teams that work on these things today are not just physicists anymore, right? It's material scientists, it's computer engineers, it's software engineers. We work on, we have physical infrastructure to build and deploy. We have educational materials, since it's sort of unfamiliar or alien to a lot of our target users. And so like the kind of the workforce that exists at a team like IBM Quantum is not recognizable from a single sort of academic department, right? And that's part of the excitement of working in this area, is that you get to sort of rub shoulders with people from different disciplines. So, you know, you get to learn from a microwave engineer or whatever it is on the particular problem that actually is at hand. But if you're thinking about training students to enter this this field, like it can't just be a physics education, or I would say it can't even just be just a computer science education, right? There's different specialties that can approach various aspects of the problem of building better quantum computers, and they come from many different fields.
At Naval Nuclear Laboratory, we consider offering positions for quantum computing specifically in regards to algorithm development. We recently had an intern actually complete this past summer developing a quantum computing software package as this intern project. We would also look at positions related more to quantum sensors, and more broadly, quantum background in general is appealing to us for areas of material science or electronic structure theory, other atomistic techniques. We regularly hire in that area.
From my experience, of course, it's not, you know, as big of of projects as IBM or anyone like that, but when we get into a specific field or working on a specific project that we need people of certain expertise, we, like, you know, for instance, some of the newer quantum projects we're looking into and researching right now, one of the first things we would do is look for someone who specifically has quantum training, not just, like they're saying, not just in physics or just in computer science. We already have those guys, but someone who has that proper mesh or some other types of training is definitely very useful.
Yeah, this sounds very much in the spirit of the NSF research traineeship programs that are supposed to, you know, spawn new interdisciplinary research at the graduate level. It might be something that PQI thinks about because there's certainly a need, and I think that we have the right mix of faculty in this area to maybe address that even beyond what's already happening within PQI. So it sounds like there's a big demand. Sounds like there's lots of opportunities for internships for students, which is great. And hopefully, you know, the interactions that we have will lead to longer term collaborations and relationships with PQI. We have another question from the audience. Yes, please.
Yep. So if, for example, I'm somebody who has who's slated to have a pretty good, solid physics background. I'm a physics PhD student. You guys were talking about a nice mesh of computer science and physics skills. If we have, you know, if somebody has like this degree that's focused in physics, can you be a little bit more specific on what kind of CS skills they should gain? And if you can, mention specific courses that you would like them to have under their belt.
So,
let me just make a comment, because this might come to a little bit related to another question I have, which is more from, like, let's say the continuing education or upskilling education, that you may have already people that are trained in a specific discipline, but they need to learn the language, right, of quantum, what's the approach maybe from the physics perspective of what those key fundamentals in something like computer science would be, where to start?
That's good. So I just jumped to answer this question because they sort of send us the questions beforehand, so I had an answer prepared for this one. So hear me out. We do offer, like, as continued education programs for other government agencies, such as the Air Force Research Laboratory. They're already very well prepared, high skilled engineers, physicists, computer scientists, which are looking for this combination, right? And in the meantime, while the first batch of quantum computer scientists graduate from Pitt, I think that everyone is asking themselves the same question: how do you retrain or like just further develop those professionals that are out there to feed this industry? I'm gonna shameless plug and mention our class at Carnegie Mellon. So we developed a class on quantum optimization and quantum machine learning. Usually, actually, I see a couple of people that have taken that class in this audience. So there are offerings from the Software Institute at Carnegie Mellon. There are courses here at Pitt. I think that we are all starting to prepare in order to get this workforce ready. To your very, very specific question on what should a physics major like go after, it really depends on what you like. I think a little bit of computer complexity classes won't hurt you. But besides that, it really depends what you want to do. If you want to specialize in chemistry, if you want to specialize in optimization, there are different skills that you need to learn. Let's see. Yeah, I think that's
Okay.
I think there is an expectation whether or not you'll end up doing complexity theory and gate circuit models or not, that you'll be aware of it if you call yourself somebody in quantum computing. So to answer your question, taking basic courses on NP completeness, Turing machines, things like that, to understand what it is that computer science folks thinks is hard, right? What is that framework? And then what can quantum computing do? I mean, why is, let's say, the HHL algorithm, or why is the Shor algorithm so exciting? So a couple of classes on classical complexity theory, followed with a class on quantum computing that builds on algorithms of that type, might bring a physicist closer to, I think, what a quantum computing community will think is something you should know. Now, to David's point, that does not mean that you can actually solve an industry problem, because that's not how these courses are geared. If you are interested in solving something that is computational, then the course that we developed at CMU, NASA and USRA actually took all our videos and made it part of the Feynman Academy, so that they could train their physicists and their quantum computing people how to solve these kind of large scale problems using, let's say, quantum inspired computing. So, but from a basic pedagogical perspective, I would think if you want a job at IBM or things like that, knowing computational complexity and this quantum algorithms might be somewhat expected.
So for us, if you're talking about physics in general, in terms of quantum applications for computational quantum mechanics, we would really just be looking for some experience with some language. We have continuing education opportunities as well. We have people come in, they might know one language and need to learn another, so they get the opportunity to go out and take courses for that. I think the only other requirement would be the ability to work in a professional coding environment, but you kind of pick that up on the job as well. So that's a little bit beyond the exact quantum computing application, but it still be quantum related, because we do have interest in doing calculations that are quantum mechanically based.
And from my side, which is very different than these guys, I wouldn't be able to say what what classes to particularly take. Like they covered that quite nicely. But I will say that whenever I'm looking to hire someone for a specific interdisciplinary whatever, I usually find them through their papers. So if I'm looking for something very specific, like someone who's really, checking the boxes, if I see someone who put out a paper that's kind of touching the subjects that I want really well, then we start to reach out to whoever it is and start, and then we get a few candidates, and then it's more pinpointed type of focus on that stuff, because we don't have a ton of people we're hiring. We want 2 or 3 really good guys. So that's my thoughts on it.
Blake, did you have a comment or?
Sure, maybe just to clarify what I meant earlier about these interdisciplinary nature of quantum computing. There are very few individuals that sort of enter quantum computing, or even to this day sort of are trying to be broad within quantum computing, right? There's no one that's an expert in materials science, in gate dynamics, in Hamiltonian engineering, in in all these different things, right? So like most of the practitioners today become specialists within some aspect of it, and I think that's a perfectly reasonable strategy. Is someone like you have some passion of this, recognize that the surface is huge, you have some passion, follow that, and use that as your entry point to make an impact in quantum computing.
Thank you.
Yep. So I work a lot with computer scientists, software engineers, developers, and trying to bring them to being either quantum aware or maybe proficient in it, right? And we do that by kind of going through and using quantum simulators to get them used to using a lot of those traditional, if you can call them, quantum algorithms, right? So like Deutsches, Grovers, Shor's, and a lot of the students are now starting to look and try and find places where they can be software engineers and developers. Is that enough to come and work with you as far as a software engineer? If they're like trained traditionally as a software engineer or developer, then they learn some of the main quantum algorithms. Is that hireable to you? Would you like them to have something more? Are we doing too much?
And try to take it first, since I do hire a lot of software engineers. Any prior exposure to any part of quantum is usually enough to give someone a hook that lets them get successful. Invariably, someone's going to be learning something new, right? Like I've been hiring people to work on compilers as we've been rebuilding our compilation stack to use LLVM. Most of the people sort of understand something about like gate dynamics and like what kind of control signals they're trying to produce are not also experts in traditional compilation stacks. But you have, so I end up assembling teams of people that are sort of more comfortable with physics, with people that are more comfortable with the traditional like compiler engineering to be able to make that work. But some of that has like demonstrated some activity, whether it's like even just taking some course that involved Qiskit or one of the other packages that sort of gave them some foundation of like what they were building this for, often helps sort of unravel the conversations when we're saying we need to build this thing and like why and what's the next why behind that one, so that we can sort of figure out what the actual thing is that needs to be built. Is one of the things we look for when we're looking for candidates.
Okay, thank you. Any other comments on that? And we've got another question from the audience.
Yeah. So obviously, I mean, these kind of commercially available quantum technologies are fairly new in the market. But I'm sort of curious to know, has your customer base, what is it primarily, academic institutions, primarily industrial institutions, and have you seen kind of that mix change over time? Are you seeing any trends in who your customers are, maybe for lack of a better phrase?
Good question. Do you want to start, Blake, and then?
Sure, I'll start again. I mean, I shared earlier this morning the list of members of our IBM Quantum Network. which sort of covers is very broad in terms of where we see interest from industry and academic and so on, right? I don't know that I know enough off the top of my head to tell you how those trends have changed over time, but I guess I would say that the interest is very clearly initially primarily academic, and more industries have gotten comfortable with the idea that this is something that that they want to invest time and effort and resource into learning. So I think it's safe to say we are seeing growth in sort of industrial uptake.
Joshua, do you have a perspective on that from customer base?
You said my name, sorry.
Yeah.
Couldn't hear you. Okay. So the question was, I want to make sure, could you reiterate the question again real fast?
Yeah, I was just kind of curious to know what your customer base is right now, academic institutions versus industry, and have you seen kind of that ratio change? Like the first speaker just mentioned, seeing more industry players kind of enter after originally mainly being academic. Or are you seeing the same kinds of trends, or do you see different trends in your customers?
Yeah, so we are, R&D based, so we don't have like customers, but we typically work with, we try to follow what we're good at, but at the same time, you have to find what fits them, what someone's going to want. And, like you can invent something really great, but no one wants it. It doesn't really matter. So obviously we follow some of the industry trend type of things with our stuff. And there's quite a bit of interest in the quantum side. It wasn't for a long time. Like that's one reason why we leaned into a lot of our, the analog computing type stuff that we were doing. And we discussed, entering the quantum space for years. But a lot of the industry people, especially investors and things like that, were a little scared of the uncertainty. And because it's still a gamble in the R&D space. So that's changed a lot. And then, but also there's been an increase on, grants and things like that, especially with the recent, the CHIPS, I forget the name of it, thing that was signed recently. And so there's an expansion overall, but I would say industry has gotten a lot less scared of the investment side of that, at least. So.
All right, thank you. See if we have any other questions from the audience. Okay. Oh, we've got another one.
This is kind of a naive technical question, maybe for the people that are working in the IBM computing space. But is there any sort of collaboration between industry on like quantum networking, quantum information transfer? Because it seems like the future of quantum computing is kind of harnessing a bunch of smaller quantum computers to get larger quantum volume, for example. Is there any sort of ways of communication between IBM and Honeywell's technologies or IonQ's or anything like that, or are they all pretty specific to their own technology approach?
I mean, sharing quantum information between computers has been a topic that's been getting increasing interest in sort of the quantum communications, quantum networking space. But the specific technical challenges about marrying two different qubit modalities basically requires high efficiency transducers on either end of the link, right? You may agree that we're going to use telecom wavelengths for the interconnect, but then I got to convert my microwave frequency to that telecom frequency, and they got to convert from theirs to, sometimes in the ion traps, like their clock states they're using to store quantum information and are also microwaves, but at rather different bands. And so it's not. It's pretty clear that you need to have two rather independent development efforts in order to kind of complete both ends of such a link. I will say that there is maybe not industry to industry collaboration, but there are, one of the NQI centers specifically has a focus on quantum communication, and we're involved in such a project that's with UIUC and University of Chicago that's studying various different kinds of interconnect and conversion for similar reasons.
Okay, thanks. Great question. So I might ask another question I'd like each of you to respond to, and that's really now that you've learned hopefully a little bit more about PQI, maybe you could provide us some advice on what role you think an organization like this can play, and where we have a unique opportunity to forward this particular discipline. I mean, obviously the fundamental research that you saw at the poster contest and all this, the student research and faculty research going on, but give us some advice on what you think PQI could do to help with this ecosystem that's rapidly growing in the US. So maybe we'll start at the other end of the table, and you can speak on behalf of the.
I'm a business school guy, so demand generation to me is more important than cost cutting and so on. So one of the exciting things about doing this tutorial this time, I mean, Josh, you were there, hopefully it was useful, and you know, you guys will come back with new people in the future year, is communicating what this is, I think, to a broader audience. I think people who are already physicists and computer scientists maybe can catch on, and it can also differentiate between the hyperbole and reality. I feel that PQI can serve to educate, and we start in the tutorial to say, you have a STEM background. I mean, you're not a poet, let's say. I mean, unless you're a poet and a STEM background, but and so what, you know, we can teach you a little bit about it. So I think broader communication to a wider audience about what quantum, and not just computing, but what quantum communication is. I know we didn't talk much about it in the panel, but I think quantum communication is at least as exciting, if not a bit more, than kind of quantum computing. And even giving them tangible examples of what a quantum sensor is and how is it different from a regular sensor. And I think one of the examples in the tutorial somebody had brought up, I think it was Tom, about some mirrors in LIGO where you can reduce the noise through kind of correlated entanglement so that you can get much better precision of the gravitational wave. I mean, I think giving concrete examples that lights up people will be good. And to me, getting, you know, who holds the budget? I mean, they're basically MBAs in wealthy corporations, right? And we have to get to them if you want them to invest their people and their money into quantum, then they should feel that, you know, they understand something. So I would think that PQI can be, I mean, we are educators, right? I mean, so, you know, we can communicate to them, but we can also be a credible communicator, you know, because we are not like BCG trying to get a consulting deal. I mean, right? So, right? We can just say, look, this is what it is. So I think PQI can therefore serve the purpose of educating kind of, you know, I think non-technical people. That's what I would say.
Yeah, that's a great point. I'm gonna mention something else, and is PQI counts with an invaluable resource compared to other players in this business, which is the people itself, right? I mean, the students are the, I would say, one of the most valuable assets that PQI has to offer, and just bring them closer to the industry that is so interested in these skills is something that maybe PQI could play a principal role there. So the sole fact of let's say getting close to these QEDC, these quantum I don't remember what it stands for, but it's this consortium that pretty much everyone in the industry is in there, and they have all these job offers. So PQI getting closer to that would be like a good move.
Economic development.
Yeah, exactly. Quantum Economic Development Consortium. I would say just making this connection students to industry is a role that PQI is in the perfect place to play. So that would be those are my tiny advice.
Yes, I agree with my colleagues here on everything you guys have said. Additionally, I do think that you know, I actually a friend here is involved with the with PQI, and that's how I actually heard about PQI, because I'm not in the area or anything like that, like physically. However, this is, you know, you're doing a lot of things right. I will say that. The education course, the tutorial was excellent. Like it helped a lot. I'm like, we're in the space, but the space is so, you know, there's so many granular details of things that you can always learn more about. And then you know, is it Sridhar? I want to say it right. You're talking about using the you know, doing classical computing, but with the quantum mindset, essentially. That was excellent. It really kind of opened some stuff in my mind personally, and that's really good. So that's a huge thing. And then the other is being able to listen to talks, you know, look at the posters and things like that, to kind of, because that's, again, we find people who kind of pinpoint on certain things that we like or need to work on, and then we like to collaborate with different academic groups in other ways. And we've spent, you know, more than $5 million with different institutions, whether it's Georgia Tech, Fraunhofer in Germany, DTU in Denmark, and actually Liquid Crystal Institute at Kent, fairly nearby. And we worked with all these different groups, and we would end up you know, financially either supporting some students to help work on some stuff, working directly with the university. There's so many different ways to do that, but you have to find the right people, and being in an environment like this when you're trying to work on something like this is a big deal. I guess the suggestion I would say is maybe finding more ways to have direct conversations. Like, for instance, I had a great time last night, specifically having a dinner with some students, and we just kind of got talking, and now, like, I recognize them, and I recognize their names, and I'm going to be looking up some of their stuff. So that little bit of cohesive environment is beneficial. So, you know, more of that, more of being able to talk with each other is really good, in my opinion. But it has been already very beneficial, and there's a couple different groups or professors that I'm interested in working with potentially in the very near future. So that's my thoughts.
Thank you.
So we first got acquainted with PQI through the 2020 seminar series in the summer that was publicly open. We had found that, and a few of us watched that series while we're all stuck at home, and we found that very useful. And, you know, continuing with those types of events, I think would help with engagement and, you know, allow us to see many different topics across the quantum field that are ongoing. In addition to that, one of the things we've been discussing recently are boot camps for either quantum algorithm development or quantum sensors, not combined, but separate ones for each. On the quantum side, you know, things like, how do you make a quantum algorithm? How can you transform that into a tool? What's the state of the art in the field right now? On the quantum sensing, along the same lines, the theory, what hardware is involved? How's that hardware work? How do you set up a laboratory space? How does that laboratory space differ from a traditional laboratory space? Setting up an experiment, how does a experiment with a quantum sensor need to differ, if at all, from a traditional experiment? Kind of the basics that you need to set up your own lab in-house.
I guess one unique thing I would say is that for like researchers and PIs to not be afraid of directly pursuing projects in the quantum computing hardware space. To not let the sort of the existence of maturing programs from IBM and others discourage you from trying to make advances kind of in the foundations or fundamentals about how quantum hardware is built. You may not be able within your lab to build large-scale processors, but you can still change and have impact on the fundamentals of how those things are built. And I would just, as an example, right? CMOS is now a very mature technology, but right, like even some of the fundamental advances in how we build transistors still come from academia, right? As one example was the development of high-K dielectrics came from academia in the early aughts. So even 50 years from now, a fundamental advance can happen in an academic research lab. So don't be afraid of hardware.
Okay, great. That's extremely useful. So I have, being a voice for the community and a balanced voice, workforce development, networking, webinars, boot camps for educational purposes, and keep pushing fundamental sciences. So that's great advice. We're just about out of time. I want to just see if there's any other questions from the audience. And if you're online, I am looking at the chat as well. Okay. If not, I think we're pretty close to the end, and maybe I'll just go ahead and thank our speakers and our panelists for their time and your very valuable advice. We certainly appreciated having you join us during these 3 days, and look forward to hopefully future interactions with you. So let's thank our panelists. And Rod, do you have any other comments or questions? Oh, we were. Okay. I apologize. I had I had 2 to 3 on my, I maybe have an old agenda in front of me. So maybe I will ask maybe one more question just to add a little fun. What's maybe one new thing you learned, or one of the most exciting things that you learned while you were here? Could be scientific or through the poster sessions or any of the talks. Maybe just give us a little nugget of something that you picked up from your interaction.
I thought physicists were very boring people. I now think they're reasonably fun people, I think. So, and I hope physicists who thought business school people are not worth dealing with would likewise feel that, interacting would be good. But no, I mean, for example, I really like this talk about the future is analog, because, I've been looking for room temperature, light based thingies. Just to give you a little background, I created a prize in my undergraduate institution to build this poor man's sizing machine. And one of them built a time multiplex system, and one other group built a spatial system using, optoelectronic stuff. And both of those machines cost less than $1,500, built by undergraduates, and outclasses D-Wave today on max cut and number partitioning. Obviously not Gurobi, because it's a classical machine. So to me, what PQI can do, because all the people are involved, is find it easier for me to find, you, for example, that I happen to find you are just giving a talk, as if I wanted somebody who cares about photonic computing, right? Find the person. And I was also interested in this flow K engineering, and I've been asking people around to say, is there somebody at PQI who knows what flow K engineering is? So I think meeting people who actually do the things I want to do, and then I think what PQI can maybe do is find it easier to find them. I think would be great. Yeah.
Thanks. So physicists are not boring.
This is not as
Thank
boring
you.
as I originally thought. Let's put it that way.
Not as good.
So I'm a physicist and I worked with Sridhar for 3 years during my PhD, just as a background information. So, yeah, I would say I will agree with you. The last talk on photonics computing was very exciting because we are involved on these NSF expeditions on computing for also other kinds of photonic devices called coherent icing machines. So seeing this other application was very exciting to me, and I think that for me was a very interesting talk. I would say that there have been several talks that I have really enjoyed during this conference. The NSF talk, for example, was great. Seeing how the software improvements can buy you orders of magnitude speed ups, which are terribly hard to achieve in the hardware. That was something that was very aligned to what me and my group do. So that it was nice to hear it coming from somebody else. And talking to the students, I think that has been one of the most enjoyable parts of this conference.
Yes. One thing that struck me from the entire overall experience was until you're in an environment like this, you see a lot of it from the outside, in a sense, where you're reading articles and you're reading papers and all this kind of stuff, and it feels like the quantum space is very busy enough to where it's like it's going to be hard to find a spot in there, kind of like you were saying with the academia having innovation, pursuing something like even CMOS having innovation, even after it's been established for a long time. We seek out innovation in our company, and it's like you find certain fields that are incredibly saturated, or at the current status, and you get a little bit leery of jumping in and having to compete with all of that on the innovation stage. And after being here this week, I'm seeing how much opportunity there really is in the space, and how there is a lot that's going on, but there's so much more that can go on. And that was more eye-opening than I expected. Also, the students, that was a really good thing. And the last talk about the photonics, we're all going to be like fighting over hanging out with you at the end, but that's like extremely in my field. Like that was right on, like everything he was saying, I was just like soaking it all in. In fact, I saw that talk was going to happen, and that I was going to be here just for that, if nothing else already. And so that was I was very happy with that. So there's quite a few things, but just the scope of what's going on the more cutting edge type of innovations and research and everything, it was encouraging to see how much there needs to be done as well.
So I didn't actually have an opportunity to attend the rest of the week, but some of my colleagues who did have a chance to attend seemed to get a lot out of this event. I think having events like this in the future would be good. In particular, they noted some talks on quantum sensors, in particular NV center diamond sensors seem to be of a lot of interest.
I guess one surprise for me, the thing I learned, was the extent to which machine learning has kind of taken over the field of computational chemistry or computational material science. It's something I'd kind of heard peripherally at some, I've recently had the opportunity to also start to interact with the HPC community. And there's some sort of conventional wisdom in high performance computing about sort of all computational workloads that exist on high performance computing being able to reduce to just accelerating 7 different fundamental computational kernels, like the 7 dwarves of HPC. But someone gave a talk at one of these HPC conferences where they said it's no longer the 7 dwarves, it's just machine learning now. It's taken over all the rest. And that was a very general statement, but it was very interesting to see that in practice with researchers sort of leaning on that as a tool to really change the way that they do their work.
Okay, let me see if we have any other questions. Okay, if not, I think this is a good closing point. Let me just make a few announcements before we thank our panelists again, but we will have a break and be back at 3:45 for the introduction of the public lecture. So if you might see that the panelists have a copy of the book as a thank you present for joining us today. And I look forward to seeing everybody back here at 3:45 for the public lecture. So thank you again.